Okay. Um, Last little dilemma of sorts. Um, so when I looked at the schedule of what I'm supposed to cover when, um, the schedule said that last week was when I would cover spectral methods, periodic boundary conditions, which is what I did last Tuesday. And that'd be the only thing that week. And then this week would be on spectral methods, non-periodic boundary conditions, split across Tuesday and Thursday, but I covered that last Thursday. So in terms of what to cover, I'm a whole week ahead. Also, the material that I have covered takes us up to all the way through homework problem 5. When I don't think I've answered a single question on anything beyond homework problem 1. What?
I'm on 2.
Okay.
We were supposed to see that in the research meeting.
Oh, right. Okay. Oh, that's what you were going to bring up for. Okay. Yeah, because option number 1, which is the least desirable option, in my opinion, is to continue covering stuff because I don't want to get any further ahead than already in. I can certainly wait till next week. What I would prefer to do is see what's what in homework, and if anybody had spent on any time on it, then that would be ideal. So thank you.
I have the stencil for number 2, and I have kind of covered the math part of it, where I am lost when it comes to just start writing code or translating it. So I could use some help with that, just on where to begin or how to just formulate it. I have the actual code part I can work on.
Yeah.
I just need like a little diagram that could show me like, okay, start here, because I started with just defining H value and N value, and I value, the uniform grid. So at the moment.
Okay. So to make sure we're literally on the same page. Oh, well.
So this is the second one.
Okay. Okay. One problem is you're basing this off the example I did in class with Poisson's equation. Now that example had Dirichlet boundary condition at the left end and a Neumann boundary condition at the right end. This does not. This has a Dirichlet boundary condition at both ends.
So what that I understood was the very first one will just become F1, and the last one will become F2.
Okay, hold on. Actually, I'm gonna borrow this so I can write out for everybody else. Okay. Right. Right. So, so first I'm gonna write down the 2 problems I've been contrasting. So, so the example that I had was minus UXX F U of 0. This is on 0 to 1. U 0 to A, U prime of 1 is equal to C. Okay. And then the homework problem, the PDE and spatial domain is the same. You have a given F value, and then you have U of 0 and U of 1 both equal to 0. So it's a different type of boundary condition on the right end, Dirichlet instead of Neumann, and then both right hand side values are 0. Okay, now to recap what was done in this case, if the grid x1, x2 up to xn plus 1, xi equals I delta x, IH. H is equal to 1 over n plus 1. And this is therefore equal to 1. 0 is not included because the solution is known at 0. We're solving for a solution at these points. And you end up with a system, AU is equal to F. And this is the center difference stencil. Oh, wait.
Negative was on two.
Yeah. And it's minus UXX. Okay. And one, minus one, two, minus one. And the final matrix we wound up with had minus one and one. And that's because of the Neumann boundary condition. Okay. And then U system for values of U at the point where we need to compute it. So this is an n plus one by n plus one system. And F consists mainly of just the values of the given function f of x, but then it was also necessary to add boundary terms. This was a over h squared. And then over here we had plus 2c over h. So that's how that one worked out. Okay. Now, in this case, your grid will consist only of the interior points. You still have the same definition of your x values, same spacing. Okay. You're just leaving off that right boundary point because values. What the hell is this table doing? That's rude. Not sure where else it would go though. Okay, fine. Ow. Okay, actually, I think I can. That out. Okay. So, so for solving this problem, you need the, so it's the same finite difference stencil. So minus UXX at xj approximated by minus the uj minus 1 plus 2uj minus uj plus 1 all over h squared. So that will define the entries of your matrix. And you're going to have your first and last equation. That's where boundary conditions come into play. Although in this case, the boundary terms, notice it's a constant, some constant times the boundary values, but the boundary values are 0. So this is a best possible situation where you don't have boundary terms. So your right-hand side will consist only of the f values. Okay, so what you get is you're going to have an n by n matrix A, n vector f, then U is just going to be, well, A inverse F, but you would not compute it that way. Do not use MATLAB's inv. It's backslash for solving systems of equations. Okay. And for a lot of homework problems, that's the way it's going to go. You have your PDE, you have your boundary conditions, etc. You're going to, and it's going to, but discretize, it'll become a AU equals F system of linear equations. What is the A? What is the F? Backslash, bam, there's your solution. So that's going to be routine. It's going to be the different matrix or different right-hand side depending on whether it's finite difference or spectral, or what kind of boundary conditions you have, what kind of stencil do we need? So at the very beginning of this problem, you're using this center difference stencil. Whereas in part B, you're going to use a different stencil because fourth order is called for. In Canvas, okay. All right. In Canvas, I've posted some code that'll be helpful. Diffrule.m generates the coefficients of a finite difference rule. And it relies on a function make Lagrange that constructs Lagrange polynomials. So that is posted in Canvas also. Okay. All right. All right. All right. Now, sorry. All right. All right. Any questions up to this point on what to do just to get the solution? Yes.
Is this, the last but third term, the negative UX6?
Yeah.
Is it comparable to, D2UX that we have within the problem? So
Wait.
D2UX equals 1/8 squared.
Uh,
Finite difference formula.
okay. Yeah, that's where this comes from. I just have a minus throughout.
Okay.
Yeah.
And that should be sufficient because we are only trying to compute the vector u in this case.
Yes. Yeah. Well, so that's all we're gonna do is all these problems. We get, what is u? Yeah. Okay. Other question?
It's a good thing this is not a philosophy.
Okay. Oh, geez.
But I understand, thank you.
Okay. Right. Now, once you have code double compute solution, of course, we want to evaluate its accuracy. So the other part of this is also going to come up in other problems or parts of problems. What is the exact solution? Because you're given a formula for f of x, that's a bit convoluted there. And so since you have minus uxx is equal to f, to figure out what u should be, basically want to integrate f twice and negate it. So what you can think in terms of f being the result of applying the product rule for differentiation. Because, for instance, you have phi x in one term, phi xx in the other term. You have sine in one term, cosine in the other term. So you have that relationship of differentiating one factor in a term and not the other. So that's one way to look at it. Well, now I'm wondering.
Is it okay if we just apply integration by parts?
And you can. That's well. Never done it that way, and I'm not sure how easily it would go, but Okay. Interesting idea.
It'll be kind of painful, but it's doable.
Yeah, it's like you have two terms and each one you could apply integration by parts to. Okay, this could be fun. All right, so if I have integral of sine of phi prime squared dx, well, minus cosine of phi double prime dx. Okay. So then, if I apply integration by parts to these two terms separately, then in this case, like, one of these phi primes would be the dv. And then the other part would just be the v. So now I'd have u okay. So the u part would be sine phi prime, and then the v would be the phi. And then here, phi double prime is the dv. Cosine of phi is the u. Okay. But then in this case, we'd have the okay, do it this way. This is a u and this is the v. So then I have v du. So du would be cosine of phi prime squared. Times phi. Plus sine of phi double prime times phi. That covers the sense part. It's not looking so good after all. And then for the rest of it, the term over here, I'd have minus and minus, which makes a plus, but there's a minus out here, so it'll be a minus. Okay, phi prime times the derivative of this, which is minus sign, so it gives me a plus. Sine phi prime squared. Yeah, I don't like the math. I really thought that could work.
I'm sorry?
I really thought that could work.
It's a bit-
Um, yeah, it's not. All right. So,
That was just once.
yeah, so you fit the given form of f to like, h prime plus g prime h. And so then that would mean that the integral of f is g times h. And so then you'd be able to integrate it once, and then you'll get something that would be reasonable to integrate again. Now, once you have the exact solution, the real one gets to is error analysis. Now, in the preamble to a problem, like before you get to part, before you get to, actually in part A is where you do Taylor expansion to show that your scheme is second order accurate. Just from getting a local truncation error. Now, to show that numerically, so you take the norm of your compute solution minus your exact solution, using MATLAB's norm function. Now, it doesn't really matter which norm you use. It could be the 2 norm, infinity norm. By default, it's the 2 norm. And you plot that versus H on a logarithmic scale, both axes using log. And then on the same plot, you plot H squared versus H on a logarithmic scale. When you plot a power of H versus H on a log scale, it's a straight line with the slope equal to the exponent. So plotting the error versus H squared, you should get 2 parallel lines. That's how you know that your actual order of convergence is equal to the theoretical one. And so if you get that, you're done with that part. First of many.
It's saying that we have to modify the system matrix.
Where are you looking at?
Each part.
Okay, I haven't got to that yet. Okay. All right. Everything I'm talking about here is for the part of the problem before part A, solving using a regular scheme. Okay, then part A is Taylor analysis, Taylor expansion. So parts B and C, the objective is the same. You're trying to get 4th order accuracy. In part B, you do it by changing a matrix. In part C, you do it by changing a right-hand side. It's still working with this matrix. To show different ways of getting higher order accuracy. And that's where, so part B is where my diff rule function will come into play, because you can get a 5-point stencil for the second derivative that's 4th order accurate. You can actually find a stencil in my book, section 9.1. It's listed there, but so it's a standard difference involving 5 points. Or my diff rule function will repeat it for you. Well, for any questions about this part before I continue with that? Okay. All right. Just want to check something about my diff rule function before I say anything. It's been a while. Okay, in order. All right. So using diff rule, the arguments are ins and order. Order is the order of differentiation you want. So in this problem, it's going to be 2. Ins is a vector where you indicate which points you want to use. In other words, for multiples of h that are under consideration. So as an example of its usage, diff rule using indices -1 to 1 and 2 for the order leads to this output, 1 minus 2, 1, the coefficients of the center difference for the second derivative. So the idea is, like in part B, I'm looking at the hints document, make sure you look at that. Using points xj, xj plus or minus h, and plus or minus 2h. So all those multiples of h would go here in the first argument, second derivative still, and you get a vector of 5 coefficients for the interior rows. So rows 2 up to n minus 1 will use that 5-point center difference stencil to get 4-quarter accuracy. But you can't use that for the boundary conditions because this stencil is not okay with boundary conditions because you only have 1 point that goes off the edge, and that's a boundary value. But the center 5-point center difference will have 2 points going off the edge. Can't wander that far outside the domain. You just don't have any information to help you resolve it because you only have the 2 boundary conditions. So instead, what I'm suggesting you do is use a different stencil, one that is not centered. Now, if you want second derivative, 4th-order accuracy, and it's not centered, then you need 6 points instead of 5. Generally speaking, if you want, if you're trying to compute a certain order derivative, get a certain order of accuracy, then the sum of those two is the number of points you need. It might be one less than that if you have symmetry, but here, sorry, what?
Do we need 6 points in this case?
That's what I said. Yeah. So when you don't have symmetry to help you out, you're going to need 6. So for rows 1 and n, you need 6-point stencil. Okay. For 4th order. Okay. Okay. And list in the hints which multiples of h you want for your 6 points. So where you want the derivative, like at the first interior point, it's fine to use x naught minus h because that'll be a boundary point. And then you use 4 points to the right. Now, if you work out what the stencil is for row 1, for row n, you just negate the coefficients. Because that basically you're replacing h by minus h in your, oh, wait a minute. Oh, no, that's totally wrong. You don't negate, reverse the order. I do something with that, it's opposite. When it's first derivative, you have to negate. But if the even order derivative, you don't. Right. Your right-hand side is not going to be a problem. That's going to be the same in this part. So the challenge here is setting up the matrix properly. And then you can do the same kind of error analysis, except you're going to compare your plot of your error to h to the 4th to ensure 4-quarter accuracy. And what happens fairly often when students make a mistake in something like this, they might still have a solution that converges to the exact solution, but maybe it's the wrong order. For example, what happened last year, one student did something where they forgot to divide one of their matrix entries by like h or h squared or whatever it was, in dealing with a boundary condition. And so the solution converged with first order accuracy instead of second. So one tiny mistake like that can degrade the accuracy. So that's one way of finding out that you did something wrong. So that's part B. Part C, you go back to the matrix from the first time. You change the right-hand side and it tells you what term to add on, but you're going to take your second derivative of your f. Because what you're doing is you're essentially canceling out the leading error term by putting it onto the right-hand side, because in this case, you actually know what it is. It's the fourth derivative of u, but that's equal to minus f double prime. So I figure if you know that, then why not take advantage of it and get a more accurate solution? And then part D, you have a different right-hand side. So you have to, it's a piecewise function, so you have to do a piecewise integration of it twice. And there are certain conditions that have to be satisfied, because if you integrate something twice, you're going to get two arbitrary constants, two for each piece. So it's four constants altogether. But like the solution has to be continuous, and u prime has to be continuous also. So that'll be a bit of a pain to work out on paper. And then you see how things go in that case. Look at this, I can see why y'all waited so long to get started. You do the mechanics of number 3 is pretty similar. You're integrating to get an exact solution. You're getting a different Stetzel and it's an informatrix. Yeah. Okay. So are there any questions? It's about number 2. Or any other problem for that matter. I'm not sure if everything got cleaned up number 1. So I'm going to assume that everyone is good shape to continue. Maybe not. Okay.
So in A part, I will just the data values for the x's, h, ux, and ux minus h cancel out whatever cancels out. I will be left with global transition. That should
Yeah.
be OH2 or second order accurate.
Okay. So keep in mind the definition of local truncation error, which is, well, okay. matrix times the exact solution minus the right-hand side. Which if you take the local truncation error equation, give it in the hints, I just rearranged it. But du squared of xj, that's written on the previous page, early in the problem. So yeah, so you're gonna work that out using Taylor expansions.
Yeah.
Take into account that minus uxx is equal to f, which will lead to the cancellation of a couple terms. And then you'll see, oh, LTE is h to the fourth times something plus other stuff. When you Taylor expand, you only need to go out to the, well, let's see. Well, no, you need to go further to capture the error term. So the best thing to do is take it out to the fifth derivative term. Reason why, fourth derivative could have worked, but that way you get one leading error term instead of two. Because when you take your Taylor expansions of u of x plus h and u of x minus h, you take it out to a certain point, and then you stop, and then there's a Taylor remainder. Taylor remainder is evaluated as a derivative evaluated at unknown point. The two unknown points will be different. So I don't want those in the leading error term, so push it to the next term. So your leading error term will involve a derivative of u evaluated at xj. Are there any other questions at this time?
Same sense.
Okay. All right.
Can we just stay here and work?
Actually, yes. Or leave. And keep in mind, this is also true of Thursday. I'm not gonna feel like covering new stuff then either, because next Tuesday is when I would resume with the schedule. So in the interest of simplifying matters, on Thursday, I will show up, and if you have questions on the homework, then go ahead and show up. If not, don't. That way, if there's nobody here, I can leave. So. But that tells me it would be a relatively short class, even if all three of you do show up with questions, because there can only be so many of them. So. Okay. So I'm back in it.